Today, I'll be discussing on earthquake resistant design principles. I could have just said that earthquake resistant design. I could have just omitted the term principles. No, I wanted to make it very clear to you that when we go for earthquake resistant design methods, which are normally given in the code, before that we have to appreciate the principles. And if we can appreciate the principles, then you will be able to apply the earthquake resistant design methodology which are given in the different codes, and accordingly you can implement it. Because you have to understand the principles, then you have to make the design, then finally you have to develop the drawing, and that will be recommended for construction. So these are the steps normally we follow in case of earthquake resistant design. Now, before I go into the deeper part of it, try to understand few things which you can say the lessons from past earthquakes. These are the real photographs. Sometimes you will get it in the internet. And also, as I work with different organizations for your earthquake distributing and all these things, some photographs are also with me. I have just given few photographs. You see, it's a typical reinforcement concrete column. And at the base level, if the column hinge is formed, a stick hinge is formed, what does it mean? Means this particular section here at the base level, it cannot carry any further moment. It cannot sustain any load. So, what kind of failure normally we observe in this particular situation? Just see, this is the kind of failure we observe. Okay. Now this is reinforcement of the column, but diagonal shear crack in the midspan of the column. Just at the midspan of the column is a diagonal shear crack. And why it is happening like that? How can we avoid all these things? All these things are, well understood by the engineers, researchers, and many things already recommended in the code. And by experience, the engineers also, they have understood how to handle this kind of situation. Ultimately, I don't think there is any problem in dealing with earthquake resistant design of RC structures or any other structure. You see, this is another end, that diagonal shear cracking in the midspan of the column, but it's different type. It is different. Here you just see, here you just see. Both cracked, both are collapsed. Can't use this column again as it is. So, but this is also a kind of diagonal shear cracking. This is, you see, the shear and splice failure of longitudinal segment reinforcement. You can't see here, but you see, you know that when you are constructing the pile cap or even the shallow footing, you are rather taking the reinforcement from the foundation level and you are reaching to the ground level or slightly above the ground level, and then you lap your reinforcement, means the another piece of reinforcement is lapped with the this old reinforcement. Old reinforcement means which is coming from the foundation, and you continue. But if the lapping is not adequate, or sometimes you know that in different way we manage this kind of splicing situation. But if it is not done properly, then this kind of failure is generally observed. We will come in detail about it. This is, say, shear failure in captive columns, short columns. You see, there is a beam, there is another beam. In between, this column is there. Small, very small. Maybe below this beam, there is another column, but the length is short. Then what will happen? You know that the stiffness of a particular column, you generally calculate by, in many situations, you are going for 12 bi by LQ. Right? The most important thing is that this L cube, that means if the L is less, then the stiffness will be very high. And if the stiffness is very high, then what will happen? That high stiffness zone will attract more forces. Naturally, when the more forces will be transferred in that high stiffness zone, and if the high stiffness zone is not designed for that force of the moment, then it will collapse. So that's why, you know, sometimes there is a tendency of engineers just to, you know, make some walls at the ground floor level or just providing a tie beam in between. And they think that if they can break the column length, make it shorter, they are making good for the structure. No. If they do like that, the stiffness of column will increase 12 bi by L cube in cubical terms. So you just think, and when they are doing like this, then the column stiffness increases. It will attract more force. It will be a huge moment. And if the column is not reinforced accordingly, because this extra beam is given just before that, so whatever the column reinforcement available, if it is not sufficient, then there is a possibility of shear failure or any other kind of failure like this. Now you see, this is shear flexure failure. That means there is a problem of shear. Let's suppose adequate stirrups are not there. But at the same time, there is no sufficient longitudinal bars. Then also this is possible. Then it is a shear flexure failure. Now, you see, this is another shear failure in column beam joints. It's very, very important. When you will be learning this in detail, and when you will be learning IS 13920 and how the column joints are to be detailed to achieve a certain level of ductility, then you will be able to appreciate better. But from this picture, you can easily see that the column beam joint suffered a lot and ultimately lead to shear failure. You see, this is generally, you see that during earthquake, the ground surface ruptures. And, nowadays through remote sensing, one can, monitor this kind of rupture. And they can also give you an idea about the maximum displacement during earthquake. I mean, the width of the crack, maximum. And you all know that log base 10 of maximum crack width gives you an idea about Richter. So if the crack width is more, means it has undergone a very strong earthquake, right? So the surface rupture is a very, very important aspect. In code, in IS 1893 or any other code in earthquake, if you just go through the preface, generally people are not interested to go through preface, but if you go through that preface, then you will be able to understand that what kind of study they made after earthquake at a particular place. That means after earthquake, a group of persons, engineers, they're going to that site and they measure all these things. And ultimately, they can tell you that the intensity of earthquake in Richter, or like that, what type of earthquake it is. So many things they can tell you. So this code is basically based on this post-earthquake survey data. If you go through the code, you will be able to understand it. You see, some place, at some point of time, it was in zone 2. But later on, it is found that depending on the nature of earthquake, depending on post-earthquake survey, they could appreciate, no, it is not in zone 2, it is like zone 3. So it should be upgraded to zone 3. And accordingly, the seismic map is changed in IS 1893 code. So you have to understand this. Regularly, this zonation is upgraded. And at the same time, I can mentioning here that microjonation is also done depending on a particular situation, and that will give you site-specific seismic behavior of the ground. And from there, you will be able to find out many seismic parameters which are extremely helpful for calculating the base shear. See, this is another, probably it's a bridge pier just collapsed like this. You see cracking of the ground, huge cracking. Just think about it. The left ground which has ruptured like anything, cracking of the ground. And just after huge earthquake, I got an assignment from a particular company in Kanla economic zone. It was a job of 300 crore, and there were 250 structures, and we had to classify these structures accordingly. We had to classify these structures depending on damage level, and then some structure is we recommended to demolish because you can't really go for retrofitting. It is a huge cost. Some are retrofitted, and some minor repair is sufficient. Was sufficient. So this kind of 250 structures were there, and I was the consultant in that project. Now the liquefaction. Liquefaction, you heard about it. I will discuss in detail in my future lecture regarding liquefaction. And depending on the soil property, during earthquake, the soil may lose its shear strength to a great extent. And just like a fluid. And if the soil below the foundation, if it liquefies, then what may happen? It may happen like this. This particular figure is taken from internet. See, the building is as it is. The building is as it is, but tilted. Like that. These buildings are not affected. This kind of, failure is normally we observe in case of liquefaction. Right? I'll come in detail. Because previously liquefaction was not included in the code, IS 1893, but now it is included. And I have included some numerical problems also and discussed about liquefaction in my recent book also. Now, what is the requirement of a building structure to resist earthquake forces so as to get reasonable serviceability? Try to understand. I am giving importance to reasonable serviceability at an optimum cost. That means, if you think that earthquake will take place and there will be no damage, absolutely it will be perfect. It will behave like elastic structure. No, in that case, the cost will be extremely high, and what you have to do, you have to accept a particular damage limit. That is, reasonable serviceability means everything should be within a particular limit so that it can be repaired. Suppose if the main frame of the structure is all right, everything is fine, but the walls are cracked. You can go for some kind of stitching and you can use the same wall again. So like that, but if it is beyond reasonable serviceability, then probably you have to demolish the entire structure. If you want to make it, damage-free structure, then it will be, you have to spend a lot. Even then, you can't ensure. There are many other aspects of secondary effects of. Now, these are the important aspects of earthquake. Structural configuration. Is it rectangular, L-shaped, circular? All these things are very important. U-shaped. Lateral stiffness. Very, very important. The columns are providing major part of the lateral stiffness. Lateral strength. Stiffness is something, strength is something. Strength again related to the material. Then ductility. Very, very important. The structure will not collapse immediately. Or even if, it undergoes huge deformation, huge cracking, still then, by seismic retrofitting, you can reuse this structure again. But whenever you are doing all these things, you can't deny aesthetics. You can't deny the functionality of the building, because that is totally, a subject of architects. So you have to talk to them, and finally you have to decide that, aesthetics, functionality, all these things are maintained as required and mutually agreed, solutions. That is best. And for that, you have to choose the structural system in a most appropriate way. Structural system means it may be a totally frame structure, it may be, frame structure, and also, shear walls are there, right? So, I can tell you at least one thing, that whatever you do regarding structural system, you can choose in different ways. But you have to check the load path. How the load is transferred from the top to bottom and ultimately to foundation. If that load path is not proper, which we expect from a good building, then also you will be in deep trouble. The load path is also a very important aspect. A very, very important aspect. Now, the hysteresis model is extremely important to appreciate the strength and stiffness degradation, ductility, energy dissipation, capacity of the structure. You see, you heard about all these things in physics. When a particular structure is subjected to dynamic loading, right? At a particular point, at a particular time, maybe it is under tension. But immediately, in the next second, that particular point may be under compression. And that continues. So if the material is subjected to this kind of dynamic effects, then the strength of material decreases. Obviously, if there are cracks and all, stiffness will come down. And its post-yield behavior will change. And that will result to some level of ductility which may not be acceptable to you. The energy dissipation capacity of structure. Whatever energy the loads, earthquake, wind, they want to transfer on the structure should be able to carry that amount of energy. It should not be disturbed. So that energy transfer part is also very, very important. You see, RCC structure is not perfectly elastic even at the lower stress level. That all of you all know. It is concrete is not also, homogeneous, isotropic, elastic, no. But we are considering. In most of the situation, we consider strain diagram linear. And we also, just make an assumption that plane section before bending remains plane after bending, which leads to strain diagram linear, which is also not correct in case of concrete. But if you think about all these aspects, probably it will be difficult for you to analyze it. But if you can analyze it, analyze the simple model, and after that, if you keep some kind of factor of safety, some kind of safety elements for this kind of structure, that will solve our purpose. So we will always try to go for the perfect analysis. But it is not always possible. At higher stress level, it undergoes cracking, etc. Stiffness of RCC elements will decrease appreciably, and deformation will increase drastically. But it will not collapse immediately if RCC structure made sufficient uptime. I just now I told you. But if the stiffness of structure element decreases, how much it has decreased? In recent code, they are saying that when you are going for earthquake analysis, then the beam stiffness should be reduced to a particular level. Column stiffness should be reduced to a particular level. I'm not mentioning the percentage that you know how much it is for IS 456. But regarding this particular aspect,